Let's move on to the second part of the lecture today, and that is now moving from a single player where in principle the environment doesn't change and I'm just trying to optimize my chances of getting to the goal as quickly as possible, to a position where we have multiplayer environment, multi-agent environment, where the other agent or the other agents might really try to sort of spoil your fun. So try to either on purpose or by coincidence to avoid that you go to the goal position as quickly as possible. Before we go to the adversarial search, I want to have a quick word on the practicalities of the course, because I think that was mentioned yesterday pretty quickly in the introduction, but should be done a bit more, or at least repeated now. First of all, there's a bit of a confusion about the terminology that I use between the working groups, the practical groups, and the practical consultation hours. So what is the purpose of these? In the working groups, there are 6 groups. Thursday morning, 9 o'clock, there are 2 groups. Then there's one at 1 and there's one at 3. And there are 2 on Friday. And basically what you will do in these sessions is to go through some examples like the ones we've just been calculating here in the lecture, but then do it yourself. So you get a state space, and you have to apply depth first search, and you have to tell me which of the nodes do you cover, how long is the path, and so forth. You have to maybe think of heuristics that you could apply. You could practice with the best search algorithm, and there will be a TA who explains all the things again. And maybe if someone else explains it on problems that you've just tried to solve yourself, that will help to get it a bit more in your system. So that's where the working groups are for. It's for each of you. There's one group, 2 hours. Come, I think it's really worth it. And that's basically the material, the theoretical material that will be covered in the exam. So the hope is always that if you go to these working groups and you understand everything and you can do all the exercises yourself, then you should have no problems passing the exam. Then, for the practical assignment, you will have to implement 3 intelligent agents, 3 bots. And these 3 bots will be, or 3 or 4, it's sort of, some of them you have to implement, some of them you have to just fill in a little bits here and there. That's why I sometimes say 3, sometimes 4. You have to implement some bots, and you do that in groups of 3 students. These are the practical groups. And just for our records, and for you, maybe for convenience that you can communicate within these groups as well, but you do this whatever way you want, we ask you to register these groups, these practical groups on Canvas. Otherwise, there's no need. And there's no relation between the practical groups and the working groups. So even if 2 of you go to one practical group, to one working group, and the other one goes to a different one, that's not a problem. So they're completely different things. Then there are the practical consultancies hours, the inloopspreekuur, or whatever you want to call it. And these are the slots that are marked as PR in the schedule, where there will be a TA available, and where you can, if you want to book a slot, if you have a concrete question, so you have a bug that you can't find, or you can't get your head around on one algorithm, one part of the min-max algorithm, go there to the TA. They know the code, they've written the code, they can tell you all the ins and outs of the implementational questions you might have. There are spreadsheets available. Write the name of your group to the time slot that you want to have the appointment, and you will get 10 minutes with the TA. If you can't get out in these 10 minutes, you can discuss with the TA to maybe make an appointment later or to get your more complex problem solved. But in many of the cases, the problems should really be solved in short time, I would say. So really try to work before these consultation hours so that you know, oh, here is where I'm stuck, here's what I don't understand, this is where the engine works differently to what I understand it should do, and then make the appointment with the TAs. don't worry about it if you look at the sheets and they are quickly running full. We have, for all of the slots that are now there, we can add more slots at the same time because we have 2 TAs at the moment. It's only scheduled for one of them. So don't panic if you think this is full, because then we can still always try to find extra consultation hours. We have to find out what works for you and what works for us and the TAs, because they have, obviously we want to use their time as efficiently as possible. And it's good if you come in these practical consultancy hours with your team, with your practical groups, but it's not necessary. If one of you comes and talks to the TAs, fine. Yeah? But in a way, this is an attempt to teach you, to treat you as grown-ups. So you have to sort out the problems yourself. And if you're stuck, you can come and make appointments and you get individual help. But we don't have any plenary practical sessions where there will be some teacher explaining things on a practical wise. So now can we come to the project itself. The project will be implementing these intelligent agents in Python, and that is basically because we have the game engine runs in Python. I know that this is a challenge for the computer scientists, but it's also one of the explicit learning objectives of our study program, that you learn to know more computer languages. So I think it's a good exercise for computer scientists to familiarize yourself with Python. And I think it's one of the languages that everybody should have seen who calls themselves a computer scientist. So if you have specific questions, there are links on the website. And again, if there is things that are unclear, you can also talk about it to the TAs. Finally, the programming is only the vehicle for this final project. The goal of this project is that you understand the algorithms and that you understand the impact of heuristics for your search processes and so forth. So we're not going to look at the code. We're not going to decide whether you did nice code, efficient code. It's instrumental for doing your research. And the research is about understanding the AI algorithms. Okay, end of preach. Adversarial research. So in our decision-making pyramid, where we want to have generic algorithms, so not one that works for one specific game, but generic, simple, correct, well understood, and generic. We have now thought of ways of finding the best decisions with some heuristic information, so educated guessing and knowledge of people. And now we're looking at what happens when you have other people intervening and interfering with our decision-making process. And the games are simply the best way of doing this, because the games are a simple form of multi-agent environment, but it is very much controlled, and that makes it very nice for such a short course and for research in AI in general, because you can really study specific properties of your algorithms instead of having to fiddle around with lots of practical problems in more realistic environments. So the question is, what do other agents do? How do they affect our decisions and our success? And they are studied, because they are very well controlled. We agree on the rules. There's a list of the rules, and we don't have to discuss them anymore. It's just fun. So it's good to explain I can explain to my daughter that I'm here today explaining you how to write an algorithm to win Schnapsen against her. That's brilliant. I love it. Because I can never explain to my daughter what I do in my life, apart from what I do today. So they are surprisingly hard. They're maybe not as hard, these games, as it is driving a car around, but they are hard enough to really challenge us to come up with really clever AI methods. And it's the simplicity of the rules that make also good games, that they are very complex, but the rules themselves and the actions that you can take are usually not that big, because otherwise it sort of becomes not really a nice game or very difficult to learn the game. So I probably not many of you were around 1996. Maybe around, yes, but not in a way that you were as excited as I was when this happened. So, anybody remembers? Yes. So it was a famous game that was played between the then chess world champion Kasparov, who played against Deep Blue, computer program by IBM then, and it was unimaginable that this would happen, that the computer would win against the world champion in chess. It was, at the time, it was considered to be impossible, and it was really world media news that this had happened. And the same happened then, that people said, okay, chess it's maybe not that complicated, but Go is impossible. Go is really impossible. And if you look at the computation properties of the search in chess and the search in Go, you would really agree. This seems to be impossible. Until 2 years ago or 1 year ago, when Google organized a game between the AlphaGo Go algorithm against the world best player in Go, and it won very comprehensively. Yes?
Is Go the hardest one, or is there still another one?
It's a good question. I think Go is considered to be the hardest of these board games that I'm aware of. But there could be more ones. But I think this challenge is now over. So I don't think that there will be another game where people think, oh, now this was really sort of on the horizon. In the 1980s, people said chess will never happen. And in the 2010s, people said Go will never happen. And then it happened. And that is really made a huge impact. So I tested yesterday with the Kahoot what you did with my advice to learn Schnapsen, and I know that 13 people really mastered it now, and most of you understand the basic rules, but some of you didn't. So I want to spend a little bit of time, because now we get more into the game, and tomorrow in particular, I want to briefly explain the idea and the two phases of the game, because this is the most important thing. So Schnapsen is a game with 20 cards, so not that many cards. It looks relatively simple. It has 20 cards. It has the jack, the queen, the king, the 10, and the ace, which every card has a different value. So the jack is 2 points, the queen is 3, the king is 4, the 10 is 10, and the ace is 11. And it's a trick game, so there will be 10 tricks played. There's one person to start the game, the other one has to respond, and you win the trick, which is then put on in your pile, and you count the number of points that you get at each of the tricks. There is, in the beginning of the game, you start with 5 cards each and 10 cards on the pile. One of those cards is opened, and it decides which is the trump. And it's put on the bottom of the stack. Yes? So we have 9 cards that we don't know in the pile. We have 5 cards that we can see, and our opponent has 5 cards. And then the first phase of the game starts. And that is, one person starts to play the first card. The second person is allowed to play whatever card she wants to play. If she has a card of the same color that's higher, she gets the trick. If she gets a card from trump, she gets the trick unless it is the card that's played out is trump as well. So it's always the highest card that wins the trick, and you just count the number of points that you gather. Whenever you played your card, in the first phase, you refill your card deck. So the second round, the second trick, is again played on 5 cards. My hand, 5 cards, opponent's hand, but now there are only 7 hands left in the pile that are unknown, and the one trump card that we know. And then the next, it happens again. So whoever wins the trick is allowed to play, or has to play out, the next trick. This goes as long as there is no cards left in the pile. Yeah? And then phase number 2 starts. I will get in phase number 2 in a minute. There are some special things to make this more sort of non-deterministic or more sort of radical changes. And the one is that if you have a queen and a king from the same color, and you play them out, you get 20 points. You play one of the cards you have to put on the table. If you have the king and the queen from the trump, you get 40 points. So you're very close to 66 already. If you have the jack of the color that has the trump, is on the bottom of the pile, you might exchange the card. But the most important thing is the marriage, that you can get really many points with. And as soon as you know that you have 66 points, the game is over. If you win with the opponent having no points, you get 3 points. If the opponent has no card, has less than 33, you get 2 points. And if you win, then you get 1 point. If your opponent has more than 33. And then you play 7 games at one sort of mini tournament, which we probably won't implement here. But basically, you count how many points you need to get 7 points to win the entire game. Okay, so that was up to phase number 1. At the end of phase number 1, the pile is gone. And then basically, we know which of the cards have already been played. I have 1 point, my opponent has won some points. And now I know which cards she has on her hands, if I'm clever enough. I never remember, but in theory, you can remember which cards are outplayed. So you know which other cards your opponent has. You know which cards you have yourself. So from phase 1 to phase 2, this turns from an imperfect information game, where we have the uncertainty where are the cards, to a perfect information game. So in the second half of the game, we know exactly what the cards are. Where they are on the pile. There is no pile anymore. I have 1 card, my opponent has 1 card, I have hands, she's hands, so we can play. And then, of course, in the second phase, we can't fill up the cards anymore. So we play a trick, we only have 4 cards each. We play a trick, we only have 3 cards left. In the second round, there are also different rules. That's also interesting. So if I play a color, the opponent has to answer the same color. So this is very important because it changes the dynamics of the game completely. So in the first phase, the opponent can play whatever she wants. In the second phase, I can force my opponent to play something. Okay, that was a sort of basic overview.
What if I don't have the color? Like we play.
You can play whatever you want. There is an official rule that you have to win the trick, which means that you have to trump. But I'm not sure whether that's implemented in the engine. I will have to check that. Whether our game engine implements that or not, I'm not certain. So, but in principle, if you can't play the right color, you're free to play whatever card you want. Yeah? Yes, it's the same thing as here. I'm not sure whether this specific rule is implemented in the game. Because this really changes the nature of the game enormously, because then you turn from the imperfect information game to the perfect information game in the middle of the phase. And that is very difficult to implement. So I think it is not implemented. Yeah? Sure point, yes. Fair point, yeah, you're right. So that's a very dirty complication of the game. Because when you close the stack, the rules of the second phase apply. So it's in a way, I think it can be done, but I'm not sure whether the TAs have implemented it. I have to check. Yeah?
What would you consider an important aspect of the game? Declaring a marriage if you have one, or securing at least one contract?
I'm not sure I understand the question. The game is won when you have 66 points.
Yes.
And 40 points if you have a marriage, or 20 if you have a marriage, contributes very, very heavily for this. So it's a question of strategy. What you can decide to put in a marriage, you can decide not to have it. So I always decide to not play out my queen and wait for the king to come out of the pile. But that's a question of strategy that exactly is the kind of research that we should want to do next week. What is the best card to play? Okay. So that was a short introduction to Schnapsen, because now there are three elements to the game, I think, that are interesting for us. The first one is that when you start out, it's pretty complicated and it has a lot of uncertainty. So it's a game of imperfect information, and a lot of it. The more the game goes, the closer we get to a perfect information game. And in the second phase, we are really in a perfect information game with a relatively small complexity. So in this lecture today, I'm only focusing on the second phase. And also in the implementation of your programming for this week, we focus on the second phase. So we try to win, to find an algorithm, a strategy for winning the second phase of the game. We ignore the first one. We do some random distribution up to the moment where we are in the perfect information scenario. So now, for this week, consider you have 5 cards, your opponent has 5 cards, which you know which they are, and I've already made some points, my opponent has already made some points. Can I win the game under these circumstances? So, let's step back. Yeah, sorry?
When we play phase 2, do we simply try to get the most highest amount of points, or do we try to win the last break?
No, it's about getting 66.
Yeah, but I think in the official rules, if you win the last break, you win the game, right? If neither player has 66. Yeah, it's like...
Oh yeah. If neither gets 66, yes. Again, I have to check in the engine. I don't know exactly how this is implemented, but it's a very, very good question. I haven't thought about it. Yeah.
Do we play against the engine?
So yeah, that's another very good question. The engine that we have now is only something that sort of organizes the game. So it needs as input 2 bots, 2 intelligent agents, and they play against each other. So you implement an intelligent agent, you implement one, and we can have them play against each other. We provide you with a number of intelligent agents you can play against, and you can show that your intelligence is better and more intelligent than ours. But there is, unfortunately, at the moment, not yet the functionality to play against the engine, against another intelligent agent by hand. So, personally. But this is an ambition for the future. We might be able to do this after the course, or at the end of the course. Yes?
I have a couple of questions. One is, will there be a clear documentation of which rules are actually in this engine?
Yes.
Okay. And another point is, if you really want to play yourself against your bots, you could probably program a pseudo bot which you could control.
Yeah, sure. I think this is something that hopefully the GAs will be able to do in the last week. So my hope was that we could really offer you at the end of the course an interface where you can play against your own intelligent agent. That's the ambition. I have to move on, unfortunately, because I need to get you through the min-max algorithm. So just in reference to what I just talked about, the imperfect and the perfect information game, the difference is that in chess, for example, you have a perfect overview over the position that you are in. You know where all the figures are, and in Go as well. Whereas in backgammon and Monopoly, you also have perfect information, you know where the figures are, but there's always an element of chance. So you throw a dice in backgammon, and then you are allowed to do some moves according to the element of chance. And in most of the imperfect information games that we have, bridge and poker and so forth, and this is the space that we are dealing with in the Schnapsen world, We do have an element of chance in the distribution of the cards in the beginning, but mostly we have imperfect information that we don't know where the cards are. So this is a simple game setup for which we are going to introduce an algorithm now. The min-max algorithm, we have two players. They are usually called min and max, as you might have guessed, often abbreviated with X for max and I for min. Max moves first. That might, in different games, you might also have min starting, and then. But if max starts first, and then they take turns until the game is over. This is already something where Schnaps in our game is a little bit different, because in the classic min-max algorithm, min and max always switch. So min starts, then comes max, then comes mid, then comes, yeah. But if you win the trick, you are allowed to play again. So the order might change in Schnapsen. So that's a sort of a deviation of the classic min-max algorithm. We have an initial state, and that's the initial board position, the starting position of chess, for example. We have a successive function, like in the state spaces we had before. The successive function is just the list of the legal moves of my game. We have a terminal test, and that is the game finished? So in chess, that would be the king is set checkmate. And then we have a utility function. The game is won, the game is drawn, or the game is lost. And that is normally win is +1, loses and is won and draw in tic-tac-toe, for example. And then basically what you will see now is that Max will really use a simple search tree to determine what the next move is. So this is the game of tic-tac-toe. You know that you have to sort of put crosses and circles into 3x3 matrix, and you win if you have a row or so here. If you are the X player, you lose because your opponent has managed to have the row. So the utility for this becomes -1. And if you manage to get a diagonal with your own crosses, then you win the game and you get a +1. And if you have none of those two, then the game is a draw. Yeah? And then basically we start out with the empty board, and in each of the moves, X is allowed to make a cross somewhere. So in this case, X has 9 possible moves. And then min is allowed to do a move. And min now has 8 choices, and after that, max has 7 choices, and so forth. Yeah. So in this case, we have a state space of 9 faculty. So it's rather bigger even than the one we had with Schnapsen. And now the question is, can we enforce? Can Max, the one who starts, you want to calculate the value for, can it come up with a strategy that tells me if I make this move, then I will go to win the game? And we can do exactly the same for Schnapsen now in the phase 2 that I was talking about. We start with our sets of hands. If Max, me, plays one of the 5 cards, then Min is forced to play a certain card, and I can in principle write down this game in this way. It might be that here this is not the right order, because if I'm allowed to continue, then it would be, if min is allowed to continue, then the order would change. Something to take into account when you implement the algorithm. There's one thing that might be confusing here, that you should be aware of, and that is that the diagram shows the transitions and not the states. So in principle, it would be theoretically more clear if I would give you the hands, but then it's almost impossible to read. So if I play the ace and my opponent plays the 10, then here I end up in a state where I have the 4 cards left here and the 4 cards here left. So here should be a state with 4 cards and 4 cards describing the situation we are in. So in this diagram, it's a bit different from the diagrams I've shown you before. It's namely the diagram which shows the transitions and not the states. You always have to think the states in the middle. Yeah? Very important. And then the question is, can I come up with an optimal strategy so that Max wins assuming that min does its best to win the game as well. So the assumption is now both players play optimally. And then basically the value of the min-max choice for a node n can be calculated this way. So if I'm in a max node, so max is the first one to play, then it starts with the successes of this state, and it takes the maximum value of all the results it gets back. So basically it looks at all the options, and max chooses the one which gives you the highest value. And min does the opposite. This has to be a min. I'm sorry, this is a typo. Okay. And if I'm at a state somewhere where I know whether it's a win or a loss, I know the utility, I know the result of the game, then I can return the value. So here's an example, a very simplified abstract. You play the game, you start down there, you have different moves, and you get to these final positions where you can't move any further. You end up in a 0 position, you end up in a 1 position here, you end up in a 0 position there. If you are max, can you win the game? Can min win the game? So here, in this node, it is Max's choice to choose what she thinks is the best for her. What will she pick? She will pick the 1. So here, Max has the choice to do a 1. Here is the same. She has only one option though. So she will have to pick the 0. So in this node, should pin out. So this is a 0, and this is a 1. Yeah? Now we go one level further, and this is now a min choice. So if min has a choice between a 0 and a 1, what will she choose? 0, of course. And here she hasn't got a choice because it's just the loser position. Yeah? But here, I've forgotten this one, the most important one. Here, she hasn't got a choice because she only can go to this position. Yeah? Now it's Max's choice. Which one will he choose here? The 1. Which one will he choose here? The 1. Which one will he choose here? The 1. Yeah? So for both moves of Max on this first move that he can make, he can force min so that he will win the game. So basically, this is a game that will end if Max plays optimally, we'll get a 1. And this is the basic algorithm of min-max. But there's one thing more. So I've talked about winning, losing, and drawing now. So min 1, 0, and 1. But obviously, many games don't end up with a simple win, but you can get 3 points in Schnapsen, you can get 2 points in Schnapsen for a game. And every game sort of has a different way of winning and losing. And you want to win as high as possible. So yesterday I asked whether we had any German, Austrian, or Romanian people in the room. Today I want to know whether there are any English people in the room. No English. Any Australians? Congratulations. So I'm not sure whether you follow cricket, but no, you don't. This is I lived for some years in England, and it's the only game that you can sort of that's as exciting to watch on Twitter than it is live, because the only thing that's interesting is whether a point is made or not. But this, anyways, I hope there are no cricket lovers. It's a fantastic game. It takes 5 days, and you can win in incredibly complicated ways. So I was asking about England and Australia because there is a famous tournament that's played, I think, yearly or bi-yearly between England and Australia. And Australia really hammered England last days. And they won this game by a very, very complicated score of, it should come now, an innings and 123 runs. Yeah, so that's a lot. But you need to understand what it means for a game to end in a certain way. So it is better to win by an innings and 1 point rather than winning by 300 points. So the innings is a very important thing. So the only point I want to make, the only point I want to make here is that there are different ways to measure the outcome of a game. So if you look at Schnapsen, I said that you can win the game if you win the 66 and your opponent has 58, then you get a point. If you win and your opponent has 35 points, 28, then you get 2 points. And if your opponent has none, then you get 3 points. Yeah, so you get different values. And the optimization is not only finding the one, but finding the highest value to win the game. There's also a different way of looking at this. You can also count in Schnapsen the number of points that you make. So winning with 66 is maybe better than winning with 85 is better than winning with 66. Doesn't really make sense, but it could be done in a different way, yeah? It depends. I mean, this is more sort of abstract example, but so basically we don't have a tree where we have at the end stage we have a won or loss, but we have a maximum value. So now the game with the score instead of utility is that you want to maximize. And the way this works is exactly the same. So basically I'm in a state where min wants to get the smallest value to the next level. So 3, 2, 12, and 8, 3 is the smallest one, so this one is propagated up there. 2 is the smallest of those 3, and 2 is the smallest of these. So the next choice is for max. So the best decision max can make, the best result max can get is to choose a 1 because it can get 3 points. Yeah? And this is exactly the min-max algorithm that is applied. You start with you want to calculate the maximum value of a state. So we start with a max move, and we do this by looking at the successors and give the values. So we have the max value function, which is called which looks at if it's a terminal. It takes the value of the tree that we get, -3 or +7 or whatever, and then it looks for all the successes, what the value is, and it sets the value v as a maximum of all the minimum values that it got from the level lower. So it's a recursive call for the maximum, counting the maximum of the result of the decision of what min did the level below. And obviously this is defined exactly the other way around. So the min value is determined by looking at all the max values the level below and then taking the smallest out of it. So that was exactly the algorithm that I just showed you a couple of minutes ago. So these are the two things. It's important you have a recursive call where min asks max give me the best results that max can get underneath in the search tree, and then I pick the smallest of all those. And max does exactly the same, the opposite, sorry. And this depends on the value that you get out of your game. So there is a small comment to make that this works even if min doesn't play optimal. So if min says, oh, I do some random noise, max will still win. So that is a theoretically shown result that you don't have to, so you can't play better by playing worse, in a way, if that makes sense. So the properties are it's complete, it will always find the best strategy. It has a relatively bad time complexity. It takes a long time to calculate, but the space complexity is okay because you only do it branch by branch. So now, this is what you're going to implement in the milestone. You have a depth 5, so that's pretty easy. It's relatively small search space, 15,000 nodes. In the worksheet that will be published in the next hour, there will be a step-by-step on how to start with implementing this min-max algorithm for you to do tomorrow. And then you can run experiments with the existing bots that we give you and play around with this. So that's basically what you should do until Friday evening. So now let's think of this idea for chess. And this doesn't really work. Why not? It will take too much time. Talking about too much time, I have taken slightly too much time on other things. So would it be okay if I take 3 more minutes from your lunch? So please wait with packing for 3 more minutes, and then I promise you I will finish 3 minutes late, and not more. So if you look at chess and you build the search tree, that's possible. That's very complicated because you have 24 options or 20 options per move. But you basically never know where you are. So it's far too complicated and complex to go to all the leaf nodes. So you will never know all the whether you win a position or not. So this is the sort of, this complexity needs to be tamed. And it is tamed in a way that we turn a perfect information game, such as chess, into an imperfect information game. It sounds very unnatural, but it basically means that we say, we stop looking at a certain moment in the algorithm, and then we make an estimation whether it's a good position or not. And here comes back our heuristics. So min-max requires too many leaf nodes evaluation, and in chess you can't even get to these leaf nodes easily. So what you do instead is that at a certain moment you cut off the search. You say, okay, now here, I don't know yet whether I won or not, but I can estimate how good the position is. And then, based on how good this position is, I can estimate whether I win or not. So basically, you go from the utility, which is the result that you know whether you win or lose a game, you go to an estimate again. So you go to a heuristic way. You cut off the search. So basically, you make a terminal test in the normal case that we do here. And now we say instead we do a cutoff at length 5 or length 20 or whatever. And at this cutoff point, we do some estimation of how good the state is. And this heuristic value is then propagated back to the top. So we can't say anymore, yes, we will win with 70 points and 3 innings. But we can say the chances are we have come to a node which is far better. Yeah? So the utility function is really about, I go through the entire search space to the end, and then I backpropagate the real game results to the decision-making process. Here, I go to some cutoff point, purely computationally forced to do so, and at this cutoff point, I do an estimation how good my results are, and then I backpropagate it. For the rest, it's exactly the same algorithm. So here's some discussion about the difference between using the utility, which is really the value of the game, versus a heuristic estimation. And that comes back to the question of what is good heuristics, and what is good heuristics for a game. I think that it's enough if I discuss the heuristics and the impact of the heuristics tomorrow morning at the beginning of the lecture. So that's the advantage of having lectures every day. So this part is not necessarily necessary for you to start now with the project. So I think let's leave it here. We discuss the use of heuristics tomorrow. You will get, within the next hour, we will publish the Git repository with the engine, the game engine, with some bots you can start playing around with. And tomorrow you will get a skeleton of the min-max algorithm and an alpha beta pruning bot so that you can really start implementing tomorrow. So start looking into the code, read the reader, watch videos, and see you tomorrow.